So what is continuity? Let's look at the definition. A function f of x is continuous at a being some fixed real number, if the limit of f of x as x goes to a is equal to f of a. Recall, when we first defined a limit, the limit of a function just had to be some number. Now, with continuity, the limit is a specific number, and that number is f of a, the function defined at a. If f of x is not continuous at a, we say it's discontinuous at a. Three things must happen for f of x to be continuous at a. 1. F of a must be defined. In other words, a is in the domain of the function. 2. The limit of f of x must exist as x goes to a. And 3. The limit must equal the function at a. So if one of these three things does not occur, f of x is discontinuous at a. Let us take a look at what discontinuity means in terms of a graph. Notice, in this graph, if we draw the graph from here and go along the curve, you have to do what we call pick up the pencil and start again. Anytime you have to pick up your pencil in terms of drawing this graph is a case where you have a point of discontinuity. Notice here we have discontinuities at x equals -1, x equals 1, x equals 2, and x equals 3. Let's look at the reasoning for these discontinuities. Here, f of -1 is not defined. Here, at x equals 1, the limit of f of x as x goes to 1 does not exist. This is due to the limit from the left is not equal to the limit coming from the right. We call this a jump discontinuity. Here, the limit of f of x as x goes to 2 does not exist. This, again, due to the limit from the left, is not equal to the limit coming from the right. And finally, at x equals 3, notice the limit does exist. The limit from the left is equal to the limit coming from the right, but the limit is not equal to the function at 3. We call this a removable discontinuity. Notice for this graph, we never have to pick up the pencil once. We say f of x in this graph is continuous on the interval -2 to 2. In other words, the function is continuous for all values between -2 and 2. Due to our limit laws from the previous chapter, we have the following theorem. If f and g are both continuous at a, then the following are also continuous at a. F plus g, f minus g, any constant c times f, f times g, and f divided by g when g of a is not equal to 0. Here we have another useful theorem. The following types of functions are continuous at every value in their domain: polynomials, rational functions, root functions, trigonometric functions, inverse trigonometric functions, exponential functions, and logarithmic functions. Recall from the previous chapter on limits that for all these functions we can now use direct substitution when taking their limits. Let us take a look at a quick example. Notice here we have the limit of tangent x over 2 plus sine x as x goes to 0. And tangent x in the numerator is continuous at x equals 0. And the denominator is also continuous at x equals 0 for 2 plus sine x. Hence, all we do to take the limit is use direct substitution and plug x equals 0 right into the function. So now we have tangent 0 over 2 plus sine 0, which is equal to 0 over 2 plus 0, which is equal to 0. Let's look at another example. Here let's evaluate the limit as x goes to pi of the cosine of x squared minus pi squared over x minus pi. So what we're doing is taking a limit of a composite function. And notice cosine is of course continuous everywhere. So what we can do is take that limit and plug it right into the inside function. So what we have now, this is equal to the cosine of the limit as x goes to pi of x squared minus pi squared over x minus pi. Notice x squared minus pi squared over x minus pi does not exist at x equals pi because we get 0 in the denominator. So what we have to do is some algebraic steps to manipulate this so we can take the limit. And in doing that, and factoring x squared minus pi squared, we end up with the limit as x goes to pi of x minus pi times x plus pi over x minus pi. Now we can cancel the x minus pi's, and we're left with the limit as x goes to pi of x plus pi. And now we can use direct substitution, which gives us 2 pi. So our final answer is the cosine of 2 pi, which is equal to 1. Let us now look at an example which puts continuity in perspective. For k a constant, consider the following piecewise function. F of x is equal to sine x plus k for x greater than or equal to 0, and is equal to x minus k all squared for x less than 0. For what values of k is f of x continuous for all reals? Notice f of x is continuous for all values where x is not equal to 0, no matter what k is. As for continuity at x equals 0, we must have the limit exist at 0. And recall this occurs when the limit of f of x as x goes to 0 from the right is equal to the limit of f of x as x goes to 0 from the left. So we take x equals 0 and we plug in into sine x plus k, and we end up with k. And we take x equals 0 and we plug into x minus k squared, and we end up with k squared. So now we have k is equal to k squared, which leads to k squared minus k equal to 0, and distribute out of k, and we have k times k minus 1 equal to 0, which gives us k equals 0 or k equals 1. So for these two k values, we have the limit as x goes to 0 from the right is equal to the limit as x goes to 0 from the left, which is equal to f of 0, and hence continuous at x equals 0. So now our function for these two k values is continuous for all reals.